Hello everyone. So in the previous class we were studying the maths for support vector machine and I did started with vectors, some operations which we do with the vectors. I took a vector x which can be written as x1 I cap plus x2 j cap. I found the magnitude or length of this vector, which is written as x1 square plus x2 square. Then I have also found the direction of vector, which is represented by w, and I mentioned x1 upon x, x2 upon x, where this is cos theta, this is cos alpha. Also, we did found the product of two vectors x dot y, that is your x y cos theta. Theta is the angle between the two vectors, and we did some maths here. We calculated the value of cos theta, that was coming to be like x1 y1 plus x2 y2 divided by x y, and we perform the cross multiplication here. So we got x y cos theta as x1 y1 plus x2 y2, and then I have written this in form of summation, like I equal to 1 to n xi yi, and we have used this terminology in hyperplane linearly separable data. Okay, so I told yesterday also, if you are having two features f1 f2, two classes, this is class A, this is class B, then you can separate it with a line. This is called as a hyperplane. Okay, and since we are dealing with the basic case, linearly separable 2D data, hyperplane, obviously it's a line, and the equation of line is y equal to mx plus c, which I have written y equal to ax plus b. I changed the notation, and then I reorganized this equation by putting the value of x equal to x1, y equal to x2, and then I got the value as ax1 minus x2 plus b, and then this equation will be like in this format, and I compared this with what I achieved here. Okay, so I have written like this: a dot x1 plus minus 1 dot x2 plus b equal to 0. So this can be in a format, okay, summation of xi yi. So it's a like dot product between w and x, and here w is a minus 1, that means this and this, and x is x1 and x2. Okay, got it. So this is the equation of hyperplane. And then I have also written the equation of H1 and H2. H1 and H2. We are having two classes now. Positive class and negative class. Two classes we are having. So the equation H1 and H2, what I have written is, okay, for positive class I mentioned Wx plus b greater than equal to plus 1. Then Wx plus b less than equal to minus 1 for negative class. Okay, so here y, the output, the class positive and negative are represented as plus 1 and minus 1. Okay, got it. Then we did combined these two equation to make a constraint equation. Okay, I did combined these two and written y wx plus b minus 1 greater than equal to 0. So this will be constraint equation. Okay, constraint. Why constraint? Because obviously you are having an inequality. No? That is why it is constraint. Okay, got it. So in this, later on, we got this constraint equation. And then again, I have made the diagram. Okay, like this. This is your hyperplane. This is your H1. This is your H2. This is your positive class. This is your negative class. Okay, and from here origin, here is a distance. This is d1, entire is d2, and here is the margin. That is the width margin. Okay, and d2 is the entire one, and margin is equal to d2 minus d1. That's what I have written. And we also calculated what is the value of d1 and d2 according to the coordinate geometry. That means if we drop a perpendicular distance from a point over the line, we substitute those coordinates in the equation of line. Okay, and we do follow up a formula like this. Okay, so ax plus by plus c under root of a square plus b square, and I can put the value of x and y, the coordinates here. That will be the distance. Okay, I did that. And margin, this m, by performing this, everything is present in my previous lecture. So margin I got 2 by w. This is what I got. Okay, and our goal is to perform optimization. Optimization means you require optimal margin, the best margin, which can separate the classes properly, where there should be less misclassifications, and I can separate the data points with good score, good accuracy. Okay, fine. So let me share my entire screen and tell you what we have to do next. So we got the margin as 2 by w. We want margin to be max. The value of margin should have to be maximum. Okay, so M max. This can be maximum if W is minimum. Okay, if W is minimum, then only it can be maximum. All right. So here, in order to perform the optimization, I wrote W minimum for M or margin to get maximum. Well, as you know, in optimization, we do perform differentiation. We did for linear regression optimization also, logistic regression optimization also, maxima, minima. Okay, that's what we have done. So there too, we converted the objective function into higher order. Okay, in order a way so that it can be differentiated, because if I do perform d by dw of mod of w, this is trouble. Okay, so it's better, let's take the square of this, w square. For more simplicity, we do take it as w square by 2. So all these are assumptions which we are following just in order to have simplification easy. Okay, simplify. So what I got here is w square by 2 is my objective function. I want this term to be minimum. Obviously, it requires differentiation. But there is a twist. We can't directly differentiate this objective function because just recently you have seen constraint equation. You have to work under constraint. Okay, work under constraint. It's not unconstrained equation, it's constraint equation. Okay, you got this as objective function. You want to optimize this function, but under constraint. This is your constraint equation. So optimization of this under constraint of hyperplane. Okay, so how to solve this problem? Now we are in a problem. In linear regression, logistic regression, that was not the case. We were not in any of the constraint. We were free at that time. We don't have such kind of inequality. But here we are having inequality. We have to minimize this in order to maximize the margin, but it should be done under the constraint. Okay, so remember always there are two types of optimization problem. Okay, one is constraint, another is unconstrained. Okay, constraint and unconstrained. The unconstrained optimization, this concept is same in calculus for finding maxima and minima. We have already done such kind of task. For example, you are having a function, okay, multivariate function like x square plus y square. I don't have any constraint here. I can differentiate del f by del x, that will be 2x, del f by del y, that will be 2y. And you know, in order to find maxima or minima, I need to equate this differentiation, this del f by del x, that is I'm putting like delta 1, that is equal to 0. So 2x equal to 0, so x equal to 0. Similarly, del f by del y, so that is also 0. 2y is also equal to 0, so y equal to 0. In linear regression, logistic regression, we were having the same thing, like we were solving for m and b. Okay, and they were not under any constraint. We did this thing only. Okay, but now you are now in a twist. In support vector machine, we do have this category of optimization, and we have to use some technique to solve it. Some technique is required. You can't do this direct differentiation. So what is the technique? Now this is something new thing which you haven't learned. The technique is Lagrange's multiplier. This is the technique, Lagrange's multiplier. Lagrange's multiplier are used to solve optimization problem under constraint. Okay, and according to Lagrange multiplier, what we do, for example, again, if you are having a function f as x square plus y square, and we are having a constraint equation like x plus y minus 3, this is a constraint equation, and this is my function. So according to Lagrange multiplier L, this can be written as f minus lambda g. Okay, this is how we can write f minus lambda g. That means x square plus y square minus lambda x plus y minus 3. This is equal to L. It's Lagrange. And then what we have to do next? We have to partially differentiate L with respect to x, with respect to y, with respect to lambda. This three partial differentiation we have to do. So if I perform this partial differentiation over my equation, I will be getting del L by del x is equal to 2x minus lambda, that I can put to 0, because after differentiation, partial differentiation, you have to put it to 0. Next, I can also perform del L by del y, that is coming 2y minus lambda. You can also put it to 0. And then I am getting del L by del lambda, that is equal to x plus y minus 3. I can put this also equal to 0. We can solve these three equations and we can get the value of x equal to y equal to 3 by 2 and lambda equal to 3. Okay, that's what we will get. Okay, fine. So we calculate maxima and minima of function by taking into consideration of given constraints on the variables. You are having the variables x and y. We have to take constraints, and accordingly Lagrange multiplier theorem is used to perform the optimization. If any of the function which is written like this, f of x1 x2 up to xn, if this is under constraint whose equation is g of x1 x2 dot 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 up to xn equal to 0, so this is your objective function, this is your constraint equation. Then according to the Lagrange, we do use the theorem, this theorem, where lambda is Lagrange multiplier. This is Lagrange's, okay, Lagrange's multiplier. Okay, lambda. And you have already seen the function, this function L x1 x2 up to xn, that is equal to f x1 x2 up to xn plus lambda into g x1 x2 up to xn. Okay, plus minus doesn't bother. Okay, this is what you do right for Lagrange multiplier. Okay, fine. And I have given you an example just above. Okay, so here we have to perform del L by del xi equal to 0 for all I, and del L by del lambda is equal to g x1 x2 up to xn. This is equal to 0. Okay, so whatever be the terms here x1 x2, we have to perform the differentiation of Lagrange equal to 0, and del L by del lambda will be this thing. And we have seen above, you can understand from here, del L by del x equal to 0, del L by del y equal to 0, del L by del lambda is the constraint equation, that is also equal to 0. And we have found the value of x, y and lambda here. Okay, so we have to solve this system of linear equations. Okay, this will be system of linear equations which we will solve. We did that above and we got the result for x, y and lambda. Okay, and we can find, by doing this thing, we can find the optimal value. Okay, optimal values of x1, x2 and so on. Xn we can find. Okay. Now, if you do have a question like, sir, you have used this Lagrange theorem, and we understood that, sir, you have written like okay, here in multiplication with g f minus lambda g equal to L. Okay, in the equation here you have written plus also. That doesn't matter. Ultimately, I need to perform the partial differentiation of L. Okay, and then I need to find the value of the the optimal values for these parameters. Okay, sir, you told lambda is Lagrange multiplier. What it is doing here? What this multiplier lambda is doing here? Okay, so let's talk about this multiplier, Lagrange multiplier, lambda. See, lambda helps to balance between f and g. See, we are having two functions. This is objective function and this is constraint equation. I need to maintain the balance between them. Balance means, okay, see, your function, objective function, will operate under constraint g. So, if I do any change in g, what it will impact on f? How much it will impact on f? So, if you remember one thing, and we did in linear regression, L1, L2, if you remember this thing, regularization techniques, regularization, that is penalty. What we were doing in objective function of linear regression, that was written like summation of yp minus y ka whole square divided by n. We are adding lambda L1 or L2, depends upon the type of regularization which you want to use. So this is my objective function, cost function. This is the penalty. Obviously, this is 100% in relation to what we are studying right now. Lambda was regularization parameter which controls how much penalty you can impose on the cost function. Same thing is happening here in this equation. If you see f plus lambda g, this is equal to L. This is your objective function, this is your constraint, and lambda is Lagrange multiplier. And it is controlling the impact of G on F. G, let us assume that it is a penalty or a constraint. Whatever you have to work over the margin, this is your margin. Whatever you want to do work. Okay, I need to minimize this thing. Okay, do perform minimization. This will maximize margin. Okay, but remember one thing, your maximization should follow this constraint equation. If it doesn't follow this constraint, then everything will be dismantled. That means over. You will be having more misclassifications. or you may lead to overfitting. There could be overfitting, underfitting. All right. So let us assume this is a penalty term. And how much penalty you need to impose over this objective function that is controlled by lambda. We have studied same thing in lasso and ridge regression also, regularization technique. Okay, fine. Now we do have more concepts to learn in SVM. It's not over. I'm just explaining what we are going to use. So obviously, you have to write like this: L equal to W square by 2 plus lambda y Wx plus b minus 1. This will be your Lagrange's equation, optimization equation. This is F, this is G. So this equation will be optimization equation. Okay, got it. We have to solve this equation. We will do. Okay, we will do. But before doing, let me introduce you few more terms. Well, in optimization, we have seen now we are having constraint and unconstrained. In optimization, we do have some more things. We are having primary problem and secondary problem that are called as primal and dual problem. Primal problem and dual problem. Primary problem or primal problem is a problem which is initial optimization equation, initial optimization equation. This is my primary problem. As you are seeing here, this is my primary problem. It is the original optimization problem or the equation which we do, which we want to perform the optimization, and either I need to find maxima or minima. That's what I need to find. You very well know I need to differentiate this equation, and I'm having x and y here, and I'm also having lambda here. So obviously this equation will be differentiated with respect to like del L by del X, del L by del Y, and del L by del lambda we have to do for that equation. Okay. So that's my primal problem, original optimization. Okay. I can give you a few more example. For example, if we are having an objective function as minimization of c to the power tx and constraint equation as ax greater than equal to b for x greater than equal to 0. Here x, x, c, b all are the vectors. A is matrix. So I can have any objective function. I can have a constraint equation that refers to my initial optimization problem. So let's call it as primal problem. Okay, sir, if you are having primal problem, solve it. Again, what will happen if we can't solve the primary problem? वो हम कहते हैं ना हिंदी में कि सर वो एक समस्या को हल करने में गए और दूसरी में फंस गए। ठीक है, तो ये वही है। वी ट्राइड टू सॉल्व अ प्रॉब्लम and we stuck in another problem. That is the dual problem. Okay, so dual problem is a problem which is derived from primal problem. When you solve the primal problem, you'll try to solve the primal problem. Maybe you are unable to do it. So in that particular case, you will be stuck in dual problem. And I will show you that's going to happen in the optimization equation which I have shown you. There we will stuck in this situation only. If you think, sir, the equation which you have written here, we can just differentiate with respect to x, with respect to y, and with respect to lambda, will get the solution. No, you will not get it. Okay, so obviously you will be under dual problem. Okay, so this dual problem is derived from primal problem and provides an alternate perspective. Okay, it is an alternative. Okay, it do have significant theoretical and practical implications. I can again take an example based upon dual problem. For example, okay, your objective function is B ka transpose Y, that's what you need to maximize. And your constraint equation is A ka transpose Y less than equal to C, Y greater than equal to 0. So this is your constraint equation, this is your objective function. Okay, here Y is a vector and this complete is an objective function. A is a matrix, Y is a vector. Okay, so this is your dual problem. Okay, now as we got it, the dual problem, primary problem, we do have KKT also. What is this KKT? It's a condition, KKT condition. Let me show you KKT. I hope I am available with the full form also of KKT. Okay, so yeah, let's check it here. So this term has been mentioned. Okay, if you can see the term, Karush Kun Takar, KKT condition. So these KKT conditions are connected to prior and dual problems. These conditions represent a set of equations that must be satisfied at the optimal solution of both the primal and the dual problems. So we are having some set of condition that needs to be satisfied while solving primary problem and the dual problem, and that is said to be as KKT conditions. Okay, fine. So in SVM, solving the dual problem yields Lagrange multipliers, which provides insights into the importance of individual data points or the support vectors. Obviously, we want those support vectors only. because support vectors will define the class boundary, and as much as the width between the class boundaries, margin will be more, and that's what we want a maximum margin. Okay, so obviously I need to identify the support vectors or those data points which are present in the classes. So primary problem, dual problem, they are connected through certain conditions which are called as KKT. And these conditions are the rules that are used to find the best solution in optimization problem, which are under constraint, especially under constraint. See, which are not in constraint, I don't have any issue with that. Only which are in constraint, I am having an issue with them. So the KKT conditions could be like objective constraints, stationarity, primer problem feasibility, dual problem feasibility, complementary slackness like balancing rule. So there are certain conditions. And obviously, this maths is something, a deep maths. I already told you that in machine learning, the powerful algorithm is SVM. And the maths of SVM is one of the toughest maths in the machine learning. So either we can explore KKT a bit. I did told you that these are the conditions, and we have to work under these conditions. Conditions could be objective function and the constraints. Okay, that's what we are having. We are having primary problem also. We are having dual problem also. Okay, fine. And the other terms are stationarity and the complementary slackness. That means the balancing rule. For that, we are already using Lagrange to balance between objective function and the constraint equation. So these are related. Okay, that's what they said. Na connection, connected. However, you can explore more about it. Okay, so I already told we will stuck in primary problem, and when we have to move ahead for the dual problem. And the advantages of dual problem is in terms of computation and interpretation, it can be computationally more efficient, especially when the techniques like sequential minimum optimization algorithm is used. There is one more optimization algorithm came into picture, SMO, that I will explain ahead. I will tell something about it. SMO. So you can see while solving SVM, we found many things. When we are under a constraint, we do have many algorithms in consideration. Okay, so it's computationally efficient. The dual problem. Okay, so what we have to do ultimately? Sir, we are having this equation of SVM, W square by 2, and sir, it is plus lambda, then y wx plus b minus 1. That is what our optimization equation. This is my objective function, this is my constraint. And sir, I need to do del L by del X. Okay, let's do del L by del X first. So this will be 0. Then lambda y wx. Okay, so I will be getting del L by del X. Now I do have a question, whether we have to differentiate with del L by del X or del L by del W. where x and y are the variables. W and B are my parameters. And if you remember, in linear equation and the logistic, we are having M and B as parameters. So there also we have differentiated with del cost function by del M and del cost function by del B. So why shouldn't here? So we have to differentiate with W, del L by del W, then del L by del B, and then del L by del lambda. So if I have told you previously about X and Y, okay, kindly reconsider it and convert it into this. Because W and B are our parameters, X and Y are the variables. I hope somewhere I did mention, okay, by seeing, okay, here I did mention, okay, when we are under constraints, so I did mention here, and I guess now here also not, I, okay, and I guess here, yeah. So del L by del W, del L by del B, and del L by del lambda. That's what we have to do, not X and Y. They are the variables. We have to work with the parameters. Okay, fine. So if I do perform del L by del W, what I will be getting here, it will be do 2W by 2, 2, 2 cancel, plus this is lambda y w x. So here it is W now. So okay, the result which I am going to get here is lambda y, lambda y and W, not W x, because W will be differentiated. Okay, so lambda y x, that's what I will get. Okay, lambda y and x. And if I do perform del L by del B, I will be getting, okay, so this y will be multiplied by b, lambda will be multiplied by b, rest all will become 0, so it will be lambda b, not b, y, because y, b will be differentiated. And if I perform del L by del lambda, I will be getting, okay, this will be 0, okay, and here lambda will be differentiated, so the entire term I will be getting here. The entire term I will get. That is y wx wx plus b minus 1. This is what I will get, because this will become 0 while partially differentiated with lambda. So if lambda will be differentiated here, the rest entire term will be left. So this is what I am writing, entire term will be left. And if I put this thing to 0, you're not going to get like the results. Here you're not going to get the result. You can't directly claim that x equal to this, y equal to this, lambda equal to this. Also, I have just given you the rough note of the differentiation of optimization problem. It's just a rough idea, because I will be here having the terms like xi, yi, like this, lambda I. Like this I will be having. I haven't used I notation here. Just simple I did perform the differentiation, and that's what you are seeing. However, I just managed to tell you that if we put them equal to 0, we are not going to get the final results as what is x, what is y, what is lambda. So this is my primal problem. Definitely we are stuck in this problem. We are not getting the results of x, y, and lambda. So we have to perform dual problem. So what this dual problem is, we will study ahead in the next lecture. Okay, fine. I hope you did got an idea about the maths. Okay, let me stop the recording.